Hello, everyone. In this note, we're not going to go into detail of how to do a really good curve sketch by hand using information from derivatives. Okay, so that's what the little teaser is here. To draw a graph so good that I'll think you traced a print out of Desmos, you need to consider the following things. Okay, so first thing is domain, right? So identify what domain your function is available on. Okay, this will be more important with rational and other functions. What are your intercepts? Right, so finding your roots and your y-intercept. Okay, does it have any asymptotes? Okay, does it have symmetry? Okay, this isn't critically important, but if you notice that it has symmetry, that can help you with your graph because you know there's going to be some balance there. Okay, we like to identify intervals of increase and decrease. Where is it going up and down? Okay, and we like to know where our maximum and minimum values are. Okay, from the note yesterday, right, that is information that comes from the derivative. Okay, right, if my derivative is positive, that means my function is increasing. If my derivative is negative, then I know my function is decreasing. Okay, and we can use the first derivative test to identify max and min values. Okay, we'd like to know where inflection points are. Okay, and about concavity. Okay, and this information comes from the second derivative. So to really do a thorough graph, you have to analyze three functions. Okay, the original one and these two derivatives, right? Find all their roots, because that's where the critical points and inflection points come from. Okay, so there's lots of factoring, okay, to identify all that stuff. So your factoring skills definitely need to be in good shape here. Okay, now if we were at school and needed to memorize this, you could use the mnemonic diasymic to remember those different points. Okay, but we'll just go through an example, kind of step by step, and show how it works. So here's a degree 5 function. We're going to try to sketch x to the 5th minus 8x cubed plus 16x. Okay. So we'll just go through that list in order and start writing these down. Okay, so for the first one was domain. Okay, what is the domain of this function? Okay, well, it's a polynomial function, so I know that my domain is everything. Okay, there's no issues here. Okay. Next thing is the intercepts. Okay, well, my x-intercepts are the roots, so let's start with that. So one thing I'm going to need to do with my function is factor it. So I have f of x equals, so let's have a look. First thing we hopefully notice is we've got an x on all three terms. So I'm going to common factor x. Okay, second thing we're going to notice is that this looks like a trinomial, okay, except it just has an x4 and an x squared. Okay, so depending how you were taught this in previous courses, you know, you can think for a second of this looks like a squared minus 8a plus 16, where a is equal to x squared. Okay, so we need something that multiplies to 16, adds to negative 8. Okay, that's negative 4 and negative 4. So when I factor this out, I'm going to have x squared minus 4 and x squared minus 4. Okay, those are both differences of squares, so I can continue factoring here. So I have x minus 2, x plus 2, and another x minus 2, x plus 2. So I have x, I have 2 of these, x minus 2 squared, and I have 2 of the x plus 2s, so squared. Okay. So my x-intercepts are 0. Okay, I have positive 2, and that's of order 2, so there's a double root there. And I have a negative 2, which is also of order 2, so I have a double root there. Okay. Okay, for my y-intercept, okay, well, that occurs at f of 0, but we already know that's a root, so my y-intercept is going to be at 0. Okay, next thing is symmetry. Okay, does this function have symmetry? So again, digging into our toolbox of advanced functions, the symmetry test is I plug in f of negative x and I see what happens. So I would have negative x to the power 5 minus 8 times negative x to the power of 3 plus 16 times negative x. Okay, when I run through the exponent on this, right, I have 5 negatives in a row, so it becomes negative x to the 5. Okay, same idea here. I'm going to have 3 negatives multiplied, so then that multiplies with a negative 8, so I have positive 8 x cubed and minus 16x. Okay, having a look at this compared to my original function, okay, I can common factor out a negative, and I get my original function back. So this is equal to the negative of f of x. Okay, and because of that, that means I have odd symmetry. Okay, and just to review, right, odd symmetry is point symmetry about the origin. So if this were, say, a cubic function, it would be centered around the origin, and there's point symmetry there. Right? This is 5th degree, so it's going to look a little wilder than this, but that's how it goes. That's all the information I've got from the main function. Okay, our next two parts here involve the first derivative. So we'll take a step and do our first derivative. So f prime of x is equal to 5x to the power 4 minus 24x squared plus 16. Okay, so now I'm looking at my increase and decrease and my max and mins. So again, I'm going to have to factor this, so I may as well do that now. Okay, like the last time, this looks like a quadratic, just except I have a 4 and a 2. So on the side, you could think of this as being something like 5a squared minus 24a plus 16. So I need two numbers that multiply to give me 80, which is 5 times 16, and adds to give me negative 24. Right. Okay, so those numbers would be negative 4 and negative 20. Okay, so let's start factoring that out. I have 5x to the 4 minus 20x squared minus 4x squared plus 16. Okay, equals common factor. So 5x squared, this is x squared minus 4 minus 4 x squared minus 4 and so we got x squared minus 4 and 5x squared minus 4. Okay, so in terms of roots, from my first difference of squares, right, I'm going to get plus or minus 2. Okay, from my second difference of squares, that's not a nice one, but 5x squared minus 4 equals 0. That means x squared equals 4 divided by 5. So x equals 2 over the square root of 5. Okay, so my other roots, okay, are going to be plus or minus 2 over root 5. Okay, and to help me with that, I'm going to get the decimal approximation of that. Okay, so this is roughly plus or minus 0.89, okay, for that section. Okay, now I want to see if these are going to be local maximums or local minimums. So I'm going to set up my table, okay, and start analyzing. So I've got 4 roots there. So I have from negative infinity to negative 2. I've got from negative 2 to negative 0.89. I've got from negative 0.89 to positive 0.89, from 0.89 to 2, okay, and finally from 2 to infinity. Okay. And I've only got 2 pieces. Okay, you could break this down more. You could change this to x minus 2, x plus 2. You could change this into something involving plus or minus 2 root 5. Okay, I'm just going to leave it because the test still works the same way, even if I've got slightly more complicated factors. Okay, so let's see what happens. In my first interval, so if I say I picked like a negative 3, okay, that's going to be like 9 minus 4. So this is going to be positive. Okay. This would be something much larger than that, so that's also going to be positive. Okay, in my next interval, I say pick like a negative 1 would fit in here. So my first one is going to be negative, my second one is positive. Okay, in my next interval, I believe they are both negative. Okay, and then we get negative and positive, positive and positive. Okay. So overall, for my derivative, f prime of x, okay, I have positive, negative, positive, negative, positive. So that means on my original function, oops, no prime there. Okay, it was positive, so my function is increasing until I hit negative 2. Okay, then it is decreasing until I hit negative 0.89. It is increasing again until I hit positive 8.89. It is decreasing, and then it is increasing. Okay, so in terms of my different points, it goes from increase to decrease at negative 2, so this is some kind of a max. Okay, it goes from decrease to increase to the next one, so this is going to be some kind of a min, and then a max, and then a min. Okay, so it's going to alternate between max, min, as we go through. Okay, now it's on to the second derivative. So let's just bring those back. Okay, there's my function. Okay, we knew what our first derivative was. Right? That was f prime equals 5x4 minus 16x squared. Not 16, pardon me, 24. Plus 16. Okay, I take my next derivative. So f double prime of x is going to be 20x cubed minus 48x, and the constant is gone. I would need to factor this again. Okay, so what can I remove? I can remove a 4x squared, and I get left with 5x minus, no, not x squared, just x. 5x squared minus 12. Okay, so that means that my roots are 0 from the solitary x. Okay, and from this one, let's do a little side work. Okay, same trick. I'm going to have 12 over x squared equals 12 over 5. So that's going to be 2 root 3 over 5. Okay, so this is plus or minus 2 root 3 over 5. Okay. And again, for context, let's see what that is. 2 times 3. That's about 0.69. Okay, hold on a second. That's not right. I didn't do a square root on the 5 on the denominator. My apologies. That should be there as well. So that's that. Let's try that again. Okay, that's about 1.5. Check the concavity. Once again, we're going to draw up a little table, and we're going to do the same thing we did in the previous part there. So my intervals now are from negative infinity to negative 1.55. Okay, negative 1.55 to 0, 0 to 1.55. Pardon me. Okay, from 1.55 to infinity. Okay, and I have an x. Okay, I'll just write it in a different order. My 4, okay, and my 5x squared minus 12. Okay, so in terms of my intervals here, this is going to go, let's see, x is going to be negative, negative, positive, positive. The 4 is always positive. And this is going to go negative, positive, positive, negative. Okay, so overall, my second derivative is going to be positive, and then negative, and then positive, and then negative. Oops, pardon me. Going too fast. That's not right. Okay, this is positive, negative, negative, positive. Okay. So first part is positive, second section is negative, third section is positive. No, negative. And this section is positive. Oh my goodness, no. Okay, stop for a second. I gotta slow down. Okay, negative times negative. Yes. Okay, so my derivative went from negative to positive to negative to positive. Okay, so in terms of the graph, that means this is going to be concave down. This is going to be concave up. This is going to be concave down. And it finishes concave up. Okay, so I have inflection points in each of these parts in between. That's an inflection point. That's an inflection point. And that is an inflection point. Okay, now speaking of points, before I can make this graph, okay, I'm going to have to actually figure out what all these points are. Okay, so I'm just going to do one example while I'm here to show you what I mean. Okay, but one of my inflection points is at negative 1.55. Okay, so I know there's an inflection point at negative 1.55 and something. Okay, how do I get to something? Well, I have to go back to my original function, right, f of x, and plug in negative 1.55, right? So negative 1.55 to the fifth, okay, minus 8 times negative 1.55 cubed plus 16 times negative 1.55. Like I have to go through that process for each of these locations to identify the actual point. Okay, I'm not going to show all those steps because I know you know how to plug in numbers into functions, but that's what you have to do. Right, I found all the x coordinates of these things, the inflection points, and back here it was the max and mins. Okay, right, to find the actual coordinates of these things, you have to plug in, right, what's f of -2, what's f of -0.89, what's f of 8.89, like figure out all the coordinates. Okay, so this is the summary chart that has all that stuff already done. Okay, so I had my roots, I had my y-intercepts. Okay, these are my local maxes and mins. So some of them are nice, right? These happen to be where the roots are. Okay, for the minimums for here, I have minimums at -0.89 and -9.2, and a max at 0.89 and 9.2. Okay, and here's the locations of my inflection points. Okay, so to complete our graph, we'll start adding things on here. I've plotted my roots and my y-intercept. Okay, I have a max here, 2. I have a minimum at -0.89 and -9.2. So it'll be like somewhere down here. Okay. I have a max at 0.89 and positive 9.2. So that would be somewhere up here. Okay. And I have a minimum here. Okay. I have inflection points at -1.55. So around here, and -3.97. So close to there. Okay. And then similarly at 1.55 and 3.97. So 2, 3, 4. So about there. Okay. All right. What does this all mean? Well, now we start to draw our curve. So I knew this was a double root, and I can also see that because it's a local maximum. So that means my function must come up to here and turn. Okay, it reaches this inflection point, and now it switches from concave down to concave up. It turns at the local minimum, passes through 0. Gotta be careful here. Okay, continues up till it's the max, turns around. Okay, another inflection point. So now it switches and goes up. Oh, and I didn't mark. I forgot to mark that. There was an inflection point at 0 as well. It switched there too. Okay, and that's what the function looks like. Okay, so we identified where the max and mins were. We identified what type of concavity we had. Okay, I didn't really talk about the increase decrease when I graphed it because the points kind of showed it, but right, we knew it was increasing to 2, decreasing to this min, increasing all the way through here, decreasing, and then increasing again. Okay, so those are all the pieces you need to get a really accurate sketch of what's going on in a graph. Okay, and as I mentioned, like in an earlier note, right, this helps you pin down where these local max and mins are. They're not going to be halfway between the roots. Okay, it's close, but it's not actually halfway between the roots. Okay, so in terms of practice work, okay, I'm only going to put up 2 questions here. For number 9, there's just 5 functions and it says sketch the graph. So I recommend you try to do at least 2 of them, right? Go through this process twice, get a feel for it, run it through, and make the sketch of your graph. Okay, and we know, right, you're at home using text, so it's really easy to plug it into Desmos and verify that it looks the way it's supposed to. Okay, but you're not doing yourself any favors if you don't graph it first. Right, try to graph it first, check it in Desmos, see if you got what they did, and if not, try to figure out what happened. Okay, and then number 10 is a different kind of a question. But yeah, for number 9, there's 5 graphs there. To practice the steps, I want you to try to do at least 2 of those. If you've got time, do them all. Okay, there's only 5. Okay, thank you for watching. And if you have questions about any of those, just let me know.